Hello students, in past few classes we have studied the order topology and the product topology on X cross Y. Now in today's class we are going to study next article, and it is the subspace topology. And in this article, first of all we are going to define the subspace topology, then the subspace of a topological space, and then we'll study some properties of subspace topology. So let us begin with the definition of the subspace topology. Definition of the subspace topology is: let X be a topological space with topology tau. If Y is a subset of X, then the collection tau suffix Y, which is equal to Y intersection U, where U belongs to tau, is a topology on Y, and it is called the subspace topology. Hereafter, this notation tau suffix Y we are going to call simply as tau Y. So see here how the subspace topology is defined. If X is some topological space with topology tau, and if Y is a subset of X, then the collection tau Y, which is the set of all elements of the form Y intersection U, where U is some element of tau. U is an element of tau, which means that U is an open subset of X. Then this collection tau Y is a topology on Y, and it is called the subspace topology. How the members of this subspace topology are? Members of this subspace topology are nothing but those are the intersections of open subsets of X with the set Y. Now, with this topology, Y is called subspace of X, and open sets of Y consist of all intersections of open sets of X with Y. Means if Y is a subspace of the topological space X, then the open sets of Y are nothing but they are the intersections of open sets of X with the set Y. After defining the subspace topology and subspace of a topological space, now let us study some important properties of the subspace topology. First result is this lemma. If script B is a basis for the topology of X, then the collection script By, which is equal to collection of all sets of the form B intersection Y, where B belongs to the script B. Then this collection script By is a basis for the subspace topology on Y. To prove this result, we have to show that this collection script By is a basis for the subspace topology on Y. And to prove this, we have to show that this collection script By satisfies the criteria, means conditions required for being the basis. Let us prove this lemma. Let U be an open subset of X and small y be an element of U intersection Y. We are supposing that U is an open set in X, which means that U belongs to the topology on X. And we are supposing that small y is a point in U intersection Y, where U is an open subset of X. Then we can choose an element B from the collection script B such that it contains the point Y and is contained in U. Means such that Y belongs to the set B and B is contained in U. Now as this point Y belongs to the set B and this point Y also belongs to U intersection Y, means it is in the set Y also. So as the point Y belongs to the set B as well as the set Y, therefore the point Y belongs to B intersection Y. And as B is a subset of U, therefore by set theory, B intersection Y is a subset of U intersection Y. Therefore, for every element small y belongs to the U intersection Y, there exists an element B intersection Y in the collection script By, such that that element contains the point Y and that element is contained in U intersection Y. This shows that the collection script By satisfies the conditions required for being the basis, and hence the collection script By is a basis for the subspace topology on Y. So like such, this lemma is proved. Now, while dealing with the topological space X and its subspace Y, we should be careful while using the term open set. As if A is open set in X, then it means that A belongs to the topology on X. And when we say that A is open in Y, then it means that A belongs to the topology on Y. Therefore, enough care should be taken while dealing with the open sets in case of the subspace and the topological space. Now, in the next lemma, we are going to study the situation when the open subset of the subspace becomes the open set in the topological space. So, next lemma is, let Y be a subspace of X. If U is open in Y and Y is open in X, then U is open in X. To prove this lemma, we have to consider that U is an open subset of Y and Y is open in X. Then we have to show that U is open in X also. So let us prove this lemma. Let us suppose that U is open in Y and Y is open in X. Now, by the definition of subspace topology, if U is open in Y, then it means that U is equal to Y intersection V, where V is some open set in X. This is by the definition of subspace topology. So, as U is open in Y, therefore U is equal to Y intersection V, where V is some open set in X. Again, as Y is open in X and V is also open in X, therefore the intersection of Y and V is again a open subset of X. But the intersection of Y and V is the set U. So therefore U is also open in X. So as Y and V both are open in X, therefore Y intersection V is open in X, but Y intersection V is nothing but U. Therefore U is open in X. So like such, this lemma is proved. Now next we will prove a theorem also. Statement of the theorem is, if A is a subspace of X and B is a subspace of Y, then the product topology on A cross B is the same as the topology A cross B inherits as a subspace of X cross Y. To prove this result, we have to show that the subspace topology of X cross Y is same as the product topology on A cross B, where A and B are subspaces of X and Y respectively. And to prove this, we have to show that bases of both the topologies are same. So let us prove this theorem. Let A be a subspace of X and B be a subspace of Y. Then if U is a open set in X and V is a open set in Y, then U cross V will be the general basis element of the product topology on X cross Y. And therefore, by the definition of subspace topology on A cross B, we have U cross V intersection with A cross B will be a general basis element for the subspace topology on A cross B. Now by the set theory, we have U cross V intersection with A cross B is equal to the U intersection A, it's a Cartesian product, with the V intersection B. Now as U is a open subset of X, therefore U intersection A is the general open set for the subspace topology on A. Similarly, as V is open subset of Y, therefore V intersection B is the general open set for the subspace topology on B. As explained just now, U intersection A and V intersection B are general open sets for the subspace topologies on A and B respectively. And the set U intersection A, it's a Cartesian product with the set V intersection B, is the general basis element for the product topology on A cross B. And we have just shown that both these are the same. Therefore, from this we conclude that the basis for the subspace topology on A cross B and for the product topology on A cross B are the same. As the basis for the subspace topology on A cross B and the product topology on A cross B are same, therefore from this we conclude that both these topologies are same. Hence this result. Let us consider an example. Let R be the real line and Y, which is equal to closed interval, is a subset of the real line R. Let us consider this subset in the subspace topology. Then the subspace topology has as basis all sets of the form open interval a to b intersection with the set y, where open interval a to b is an open interval in the real line. Such a set can be of one of the following types. Which are the types? Observe here. If a and b both are in the set y, then the intersection of y with the open interval a to b will be equal to the open interval a to b. Next, if only b is in the subspace y, then the intersection of y with the open interval a to b will be equal to the half open interval 0 to b. Next, when only a is in the subspace y, then the intersection of y with the open interval a to b will be equal to the half open interval a to 1. And finally, when neither a nor b is in y, then the intersection of y with the open interval a to b is equal to either y or the empty set phi. Observe that if a and b both do not belong to y, but they lie to the same side of y, either to the left side of y or to the right side of y, then in that case intersection of y with the open interval a to b will be the empty set phi. And when a and b lie to the opposite sides of y, then in that case intersection of y with the open interval a to b will be equal to the complete subspace y. So in today's class we have studied the subspace topology. We'll stop here and we'll continue in the next class. Thank you.